Atoms are often described as the building blocks of matter. We usually think of them as stable, permanent, and unchanging. But here is a surprising truth. Atoms are not perfectly stable systems. Deep inside every atom lies a tiny nucleus, where powerful forces are constantly competing, and sometimes this balance breaks. When that happens, the atom becomes unstable and begins to transform. In this lecture, we will go deeper than before. We won't just observe instability. We will understand why it happens. In the last lecture, we introduced the idea of stable and unstable nuclei. Some nuclei remain unchanged for millions of years. Others decay in fractions of a second. But that raises a fundamental question. What determines this stability? Why is one nucleus stable, while another is unstable, even if they look similar? To answer this, we must go inside the nucleus itself, because stability is not decided outside. It is decided within the nucleus. Let's quickly revisit atomic structure. An atom consists of electrons orbiting around the nucleus, and a dense central core, the nucleus. Inside the nucleus, we find protons right-pointing arrow positively charged, neutrons right-pointing arrow neutral. Together, they are called nucleons. Now here is the key point. Almost the entire mass of the atom is concentrated in this tiny nucleus. So whatever happens here determines the fate of the atom. Inside the nucleus, particles are extremely close together. Imagine packing multiple positively charged particles into a very small space. What would happen? They should strongly repel each other. Yet, the nucleus stays together. This tells us something important. There must be a powerful force acting inside the nucleus, strong enough to hold everything together. Let's focus on protons. Each proton carries a positive charge, and like charges repel each other due to electrostatic force. So inside the nucleus, every proton is pushing every other proton away. This creates a major problem. Why doesn't the nucleus break apart instantly? This repulsive force is always trying to destabilize the nucleus, so something must counteract it. That something is the strong nuclear force. This is one of the most powerful forces in nature. It acts between nucleons, protons and neutrons, and it is extremely strong, but very short range. At very small distances, it overcomes the electrostatic repulsion between protons. So inside the nucleus, protons repel each other. Strong force pulls everything together. This creates a dynamic balance. Now we can understand the core idea of nuclear stability. The nucleus is a system in constant balance between two forces. Repulsive force right-pointing arrow due to protons. Attractive force right-pointing arrow due to strong interaction. If these forces balance properly, right-pointing arrow the nucleus is stable. If not, right-pointing arrow instability begins. So stability is not a fixed property. It is a delicate equilibrium. Now let's introduce another important factor, size of the nucleus. As the nucleus becomes larger, the number of protons increases. So repulsive forces increase significantly. However, the strong force has a limitation. It works only at very short distances. So in large nuclei, repulsion spreads across the nucleus, but strong force cannot effectively bind distant nucleons. This is why, the bigger the nucleus, the less stable it becomes. So where do neutrons come into play? Neutrons are neutral. They do not cause repulsion, but they contribute to the strong force. So neutrons act like stabilizers. They increase attractive interactions. Without increasing repulsion, you can think of neutrons as a kind of buffer that helps reduce instability inside the nucleus. Without enough neutrons, the nucleus becomes unstable. This brings us to a very important concept, the neutron-to-proton ratio, or N/Z. The ratio of number of neutrons and number of protons determines stability. If it is balanced, right-pointing arrow stable nucleus. If too few neutrons, right-pointing arrow not enough attraction. If too many neutrons, right-pointing arrow imbalance again. For light nuclei, stability occurs when this ratio approximately equals 1. For heavier nuclei, more neutrons are required to maintain stability. So stability depends not just on number, but on the right proportion. To visualize this, scientists use the concept of a stability zone. This is a region where stable nuclei exist. On a graph, x-axis right-pointing arrow number of protons, y-axis right-pointing arrow number of neutrons. Stable nuclei fall within a narrow band called the valley of stability. As nuclei get heavier, the band shifts upward, meaning more neutrons are required. So stability is not random. It follows a well-defined pattern. What happens when a nucleus lies outside the stability zone? It becomes unstable, and nature tries to correct it. This happens through radioactive decay. If too many neutrons right-pointing arrow beta minus decay. If too many protons right-pointing arrow beta plus decay. In each case, the nucleus transforms itself to move back toward stability. So radioactive decay is not chaos. It is a self-correcting process. Finally, let's understand stability from an energy point of view. Every system in nature tends to move toward lower energy states. The same applies to nuclei. Unstable nuclei exist at higher energy. Stable nuclei exist at lower energy. So radioactive decay is essentially a transition from higher energy to lower energy. This is why decay releases energy in the form of radiation. And this leads to a fundamental insight. Stability is equivalent to lower energy. Or more precisely, greater stability corresponds to higher binding energy per nucleon.